Hey guys, it's Newomaster, and welcome back to another Redstone video. In this video, I'm going to be explaining how to make a binary divider. This is by popular request. A lot of people asked me on my square root extractor video to make a tutorial similar to that one for dividers, so I just said, okay, I'll do it. That was on the original video that was deleted by YouTube because they're stupid. Just kidding, YouTube is awesome, unless they are messing with the comment system or whatever. But that's another topic for another time. Anyways, I have a sample calculation, and I'm going to be showing you how to divide in binary first before we actually get into our binary division. I'm gonna build a full binary divider on camera today, probably with some bits beyond the radix point, basically decimals, so you know how to do that as well. In fact, I'll actually do a sample calculation of that later too. But first of all, let's start with this. This particular calculation, we're going to be trying to divide 25 by 5. This is 25 in binary. 16 plus 8 is 24, plus 1 is 25. If you don't know binary, you really shouldn't be watching this video. And we have our 5 here. So we are going to be just performing long division in binary. It's really that simple. So we're going to first find out, can 5 go into 110? Can it go into 6? Well, let's try it. Let's try to subtract 5 from 6. And turns out, if we subtract 5 from 6, we get 1. So we can subtract 5 from 6. And this 0 is misaligned. That's going to bug me, but whatever. So now we know that we can subtract 5 from 6. I'm going to put a little marker just so we know that we can subtract it. So right here, this marker just says, yes, we can. That was a success. We did it. Yay. And up here, I'm also going to put a 1 because we could subtract it. There's a 1. Now, if you remember how long division works, you check the next digit. So we're going to bring that 0 that we have up here down. So this particular 0, we'll move it down like that. And then we'll try to subtract 5 away from this. So let's just write our 5 in binary, and no need to write that 0 because it's just kind of irrelevant. It's just there. Subtract it. Now, obviously, 2 minus 5 is negative. So what we're going to do is, if the answer is negative, we're just not going to subtract. So instead of subtracting, we're just going to take that 2 that we've had up there already and just shove it down here. So I'm not going to write a 1 up here. Instead, I'm going to be writing a 0 because we couldn't subtract for that particular step of the division process. Now let's bring this 1 down, all the way down here. Keep going. Actually, no, we can stop. And bam, let's put the 1 right there. So now, let's try to subtract our 5 again from this. Let's build it right here. And subtract it. And obviously, we can indeed subtract it, so let's just put a little marker here again. And we get a remainder of 0. We have nothing left, which is good, because 25 divided by 5 is indeed 5. Now, since we have our little marker there, you can kind of see it, 1, 0, 1. We have our output, let's just write it up here anyways, of 1, 0, 1, which in binary is 5. Whoa, magic. Now, that was pretty simple. That's just long division done in binary. It's really that simple. But now let's try doing something that doesn't result in a perfect answer. Let's do 25 divided by 6. And I don't happen to have world edit in this world at this time because it's 1.7 and I haven't updated. So I'm just going to build it real quick, and yeah. Okay, so we have 25 divided by 6. Now, let's try to divide. Let's do the same thing we did over there. So first let's try taking away 6 from these first 3 digits here. And that should be a 1. I'm silly. So let's just do it. And as you can see, 6 minus 6 is 0. So I'm not going to build all 3 of those, so I'm just going to make 1, 0, and put our little diamond marker there because we could indeed perform the operation. It didn't result in a negative number, and a 1 up there. Now let's drop the next 0, just like we did over there. So just bring that down, make a little diamond arrow because why not? And then put our digit here. I'm going to build an extra 0 here just because. And let's try to subtract 6 from this. Well, we can't. Because 0 minus 6 is negative. It's negative 6. So the answer is 0. Because we had 0 here, so we're just not going to subtract anything from it. So let's throw a 0 up here as well. And let's bring down this 1. And there we go. Just throw the 1 right here. Move this back because OCD. And add another 0 here because it should look like that. Now let's try subtracting 6 from this again, and you can already tell that this isn't going to work either, because 1 minus 6 is negative. It's negative 5. So we have our answer. I just brought this through because we don't subtract, we just use what our first input was. We have our answer of, after I add the second 0 from that calculation we just did, 4. Remainder 1. So 25 divided by 6 is 4, remainder 1. But we don't want to stop there. That's lame. Remainders are stupid. Let's keep going. Let's say that this number here is actually 25.0000000, an infinite amount of zeros. I could select this with world edit and do / stack infinity, and it would still work. Now, let's just keep dividing. This point right here is called the radix point in binary or other base systems other than decimal. It's only called the decimal point in decimal because it's the decimal point. Whoa. So let's bring down this 0 and try to divide again. And that is slightly off alignment. Actually, no, it's not. Well, we don't need that. And let's try to subtract 6 again. And it still doesn't work. Because reasons. So, still doesn't work, so we bring down this 2 here, because we don't subtract anything, and then we add a 0 to this first digit beyond the radix point. And now, you know, digits beyond the radix point in binary are basically cut in half. Like, this is 1, this is 0.5, the next digit would be 0.25, the next digit would be 0.125. It just divides by 2 every time. Just like above the radix point, you multiply by 2 every time. When you go left, you multiply by 2. When you go right, you divide by 2. Genius. So let's bring down this 0 right here. Now, boom. Alright. And guess what? We still can't do anything. I know, it's boring. We are making a whole bunch of zeros. just wait. It gets exciting. So subtracting still doesn't work. Still receives a negative number. This time it's -2. So let's just bring down the 1 again. And these zeros. Now, if you've been paying attention, you might understand what's going to happen next time we try it. But I have to write this diamond 0 up here again first. Alright, so right now we have 4.00, or 100.00, which is just 4 right now. And so let's bring down this next 0 all the way down. It's a long way. This is a big calculation. And now we have 8 right here. Now let's try to subtract 6 from it. Huh. What do you think's going to happen? Can we subtract 6 from 8? Yes, we can. What do we get as our answer? We get 2. And we can put one of these glorious little diamond marks right here. And we can put a 1 right here. Yeah, that feels good. Feels good to have a 1 right there. So now that's 4.125 in decimal. Or in binary, it's 100.001. Now, if we wanted to keep going, we could just keep calculating. We could keep using the remainder that we have, and keep calculating with just adding more zeros here. And it will get gradually more precise the more you calculate it. A thing called precision. Now, if I actually were to calculate it out, I would get something like this. I would get 0, 1, 0, 1. Forever and ever and ever, it would be a repeating decimal, or repeating radix? I don't know what you would call that. But why? If you can see here from our, where we got our 1 right there, you can see that this remainder here is now 2. And from when we had our remainder of 2 before, right here, you can see that there are a 0 and a 1 right after it. So basically every time you get an 8, it repeats again and again and again and again. So that's basically how you divide in binary. It's actually a lot simpler than in decimal. You just divide. So I am going to cut and go to the Redstone server, where I will proceed to build a probably 4-bit divider with a few bits beyond the radix on camera, and you can see how that is done, and you can see how this translates to it. So actually, I think I'm gonna build it on this world, because that will make it easier. Yeah, let's do that. Okay, I'll see you in a bit. Alright, so now we are ready to start building. I loaded up a version of Minecraft that I am able to use single player commands on, since there isn't a single player commands for 1.7 as far as I'm aware. So I downgraded back to 1.6.2 where I have single player commands, and we are ready to build. I didn't want to build on here without single player commands because that kind of would have sucked. That's why I said I was going to build on ore. But on ore I don't have these diagrams. So the first thing we're going to do is we're going to make a just standard insta-carry adder. That's the first thing we need to start doing anything, because we need to be able to make subtractors for our divider, technically conditional subtractors, but it doesn't really matter. Those require an adder. Now I am going to be using pistons for this build, just because it makes it easier for most people to understand, since carry look everywhere adders are a bit complicated, and it doesn't really matter that much because there's a trick I'm going to use, and I'll explain it later, that completely negates the piston and any piston derps that could be present. So yeah, this is the first half adder right here. That's the carry out, and this is the propagate right here, and we need a piston right here to bring that down like so. And then for the other XOR gate, or technically XNOR, we'll just do that. And almost done. We have a very awesome adder. Just like that. Oh, I'm stupid. Not quite that far. There we go. Now we can select this. Actually, I think I'm gonna just put a slab here and this for later. I'll explain that in a sec. Now we can stack, select that point, and select a point down here. And let's make a 4-bit binary divider. So stack this 3 times. There we go. Now all I gotta do is take this and make it tile. So get rid of that, stagger. Oop, I didn't. It looks like I missed this top layer. So just like that. Now, we need to do something called conditional subtraction. Basically what conditional subtraction says is when you're subtracting 2 numbers, if the answer is negative, then use the one of the inputs. It doesn't really matter which one, but in this case it's going to be the bottom input since it's easier to bus. And so if it's negative, don't subtract. Sound familiar? And if it's positive, if the answer would be positive, then you can subtract. And that is how we're going to do our division. We're just going to make a device that does that. Now to do that, we have to figure out when a answer is negative, and those pistons are bugged. This should fix it. There we go. Yep, it's fixed. Okay. And the carry torch is also messed up. Alright, there we go. So first of all, let's just make a subtractor. Let's just make this subtract. Carry in, and let's see here. We don't actually need that. Let's invert this top input just by putting some torches here. Just like that. Alright. So this is now a subtractor. We have the carryout, which is on, which is good. Now, when you're subtracting and a number is negative, let's just make it negative by doing this. You can see that the carryout turns off. When the number is negative and you're subtracting, the carryout is off. We can use that to find when you can subtract and when you can't subtract. Right now, you can subtract 0 from 0, so the carryout is on. But let's say maybe I have 9 here, but 10 here. Well, you can't subtract 10 from 9, so the carryout is off. But if we flip these around, voila! The carryout is on, and we have our answer of 1. 10 minus 9 is 1. So, we have a subtractor that we can use conditionally using the carryout to decide if we can subtract or not, and conditionally subtract. So, these slabs here, why did I put these slabs here? Well, what we can do is we can bring these inputs of the adder underneath and around. So something like this, probably further down than that. And then, let's use a comparator, because that will be more efficient in the long run. Let's use it right here. And I think if we put a block right there, and then bust this down, yep, that will work just fine. Sorry, I had to cough. I just muted my mic. So we just bring this underneath, and now we can disable either this one or this one, depending on the carryout. So if the carryout is on, we can subtract, so disable this one, just like that, and allow this one. But if the carryout is off, disable this one and enable this one, so that it allows the bottom number to pass through and not subtract. So it's just muxing depending on if we can subtract or not for our conditional subtraction. That's pretty cool. So let's select this and stack it. I believe I can just do this. Actually, I want a repeater under here as well, since when these bus from adder to adder, I'm going to need that. And I'll worry about delay later. I'll probably just do delay off camera since it's kind of a tricky thing. Actually, maybe I'll do it on camera, but that'll be at the end when I'm synchronizing things. I do expect this to be kind of a long video. Just warning. Stack 3. Everything should be good, except for this, obviously, because that's only a one case thing, and we can replace our carry torches back to where they should be. And now we can add some of these here and bring a line on top of this that can be disabled from carryouts if need be. So when the carryout is on, this is enabled, so you can subtract. So let's just bus that to there, something just like this. Make it look nice and even. This is actually the same conditional subtraction cell that I used in my square root video, but I'm just building it again because not everyone has watched that. That doesn't need to be there, and neither does that. And now we can do the same thing down here, except for the inverse of carryout. So all we really need is repeaters. Actually, let's bring them up one block and stick it right here. Something like that, and then bus them together. That should work just fine. Yep, that looks good. And then we can connect that to the carryout. Some probably like this. There we go. Alright, so we have our conditional subtraction cell. Now let's just test it out. Let's say I have 5 minus 3, which should give us an answer of 2 just fine. There we go. There's our answer of 2. Now if we switch these inputs around, 3 minus 5, now we can't subtract. So it just gives us an answer of 3 because this is off and it's disabling the output of the subtractor and enabling just this pass-through bus underneath. And to bring that level with that input, I'm going to bring this up like that. And we should be good. Now, how do we turn this into a divider? Well, let's look at our diagram down here. So we have this first bit subtracting from the far left portion of the dividend. So what we're going to do is we're going to say that this is our far left portion of the dividend right here, this first input, just this one right here. And we're going to try to subtract this whole thing from it. And every bit we are going to we're going to basically add a new digit from this, just like we should be, since we're dropping a new digit down every time. So we're going to start with just this digit. So this is going to be our first input for our dividend. Now the divisor is up here. This is where we're subtracting from everything. This is going to be the same thing no matter what. See, when we're dividing down here, we're subtracting all these blue numbers is the same thing. We're trying to subtract the same thing over and over again. We're just shifting it every time. So what we're going to do is we're going to bus this to every divider cell I'm not going to bus it just yet because I'll have to figure out where to bus it when I'm busing it. But we can call this one of our first inputs. Let's just call it 8 since it's the 8 input. So we're seeing if this can go into this number right here. And if it can, then it will output. If it can't, then it won't. Now let's copy this cell and do that again. So let's see, make sure I'm getting everything, which I'm not. That looks like a good point. Alright, so if I copy it from, let's see, right? How do I want to do this? How do I want to do this? I see. Copy it from here and paste it to here with a shift. Now you see that we have another cell right here, like we should be. Now this one, we can just bring this down and line it up with this input right here. And we have 4. So now we're checking if we can subtract 4 in our next stage. So we're bringing the next digit down. You can kind of see it, bringing the digit down. Now, I noticed that like this one automatically checks the first 3 digits, but theoretically you would check each time and bring it down. Like, I would check this first digit first, and like basically they're just a bunch of imaginary zeros here because, well, you can't subtract anything. You can't subtract 6 from this one. You can't subtract 6 from these 2 digits together, 3. But you can subtract 6 from this 6 right here. So it's just implied that those zeros are here. 1 too many zeros. Just like that. That's just kind of cut off. But in Redstone you can't do that because it's not always the case. So yeah, that's why we have all these extraneous bits right here. And then we can just keep pasting our unit. And it's really all that simple. We have our 4 main units, just like so. Now, we do have an output right here. This output has to go somewhere, right? I mean, this is worth the same as this carryout right here. So what we're going to have to do is we're going to have to go through all of these and just simply connect this to the carryout. And I don't want to cause any issues with that adder, so I'm going to connect it to here, I think. Just like this. That torch is going to mess things up, isn't it? Yes, it will. Let's do this. There we go. Good enough. And that obviously needs to be delayed so that it matches the synchronization of this adder, but we'll do that later. Now we can bust the same for all of these. Do the same as we did for that cell. Okay, so those are connected now. And that signal should reach just fine, right? Yeah. So now we can bus the dividend bus, which is just subtracting the same thing from each cell, over through all of these. And we also need to bus these last 2 inputs as well. A lot of busing. So I'm just going to speed these up since I'm pretty sure you know how to connect buses together. It's just busing. So yeah, speed up. Alright, so I have these bussed now. This bus should work just fine. So let's just test it out, make sure that it connects all of them. Yep, looks good. Everything is connected. So now all I have to do is bring these input buses back as well. So that's just these two right here. I'll do that real quick as well. Alright, so I have all these buses done now. I just, off camera, bust them together. Didn't take that long. So we don't have the radix bits in yet, but this divider right now, as it is, will work. Now, as you can see, all the outputs, I also added repeaters on these. These are the outputs, because, as you can see, each layer checks, see if you can subtract. And as you can see from our sample divisions here, the outputs were dependent on whether or not this could subtract or not, basically. So we use this carryout, because the carryout determines if it can subtract or not, if it's negative. So, as you can see, they're all on right now, but we're doing 0, we're not entering in anything. Well, that's just because we're dividing by 0. 0 divided by 0 is infinity. You're just going to have everything on forever and ever and ever and ever. That's why they're all on. But if we were to enter something in like, I don't know, 9, and you kind of have to be slow right now because I don't have the synchronization yet, and pistons could probably block drop. 9, and then divide by 3. And we do get a block drop because pistons are stupid, but as you can see, the answer is indeed correct. It is 3, like it should be. I will be adding synchronization in this episode so you can see how to do that. And yeah, then it will not block drop no matter what. But first, let's add some radix bits, which I really just should have done beforehand because it's the same thing pretty much. Actually, I think I still have this bussing in my clipboard. Yeah, I do. It's really the same thing, you just don't have an input. Like, literally, the only thing that doesn't happen is you don't have another one of these inputs going down. Because it's always 0. That's the only difference. And you need torches right here. And I'll go ahead and copy the cell, and we should be good. And let me turn these off. Let me just turn everything off. Okay, so cell, copy. Let's find a good point to copy this from. Right there, yeah. Time, day. Good enough. Okay. And then the next point should be right here. Right, does that look good? Yeah. Alright, that should be selected just fine. As long as it didn't mess anything up, we should be good. Now let's just copy it from right. Where do I want to copy this from? Copy it from right here, I believe. Yeah, let's try copying right here. What did I do before? I don't even remember what I did before, but that should work just fine. Yeah. And then I just paste it here, right? Yeah. And that kind of messes the busing up a little bit, but whatever. So those are our radix bits. It's the same thing, except that these need to be connected. You get to see World Edit being stupid. Why is that higher up? Oh, I mispasted that one. Psh. So is this the right place? No, it's not the right place. This is the right place. There we go. That was why it was down. Alright. Now we just gotta connect these up like we did before. Connect the carryouts. And we are almost done. And then we can test. Okay, so as far as I know, these are connected perfectly, as long as World Edit didn't mess up. So let's just make a radix point. Let me use the same block I used for the one down there, just this moss stone. So our radix point is between these two. And let's divide something that's not a perfect number. Let's divide 9 by 2 instead of 3. So this might block drop and stuff because it's not synchronized yet, but it still should give us the right answer. Shouldn't it? Oh, it block dropped like crazy. That's not good. That's not good at all. Alright, so we have 4, good. But this block dropped. And then we have 0.5, good, 4.5. 9 divided by 2 is 4.5. Since this digit is worth 0.5. Because it's one digit beyond the radix. 1 divided by 2 is 0.5. 4.5. 9 divided by 2. Yay, math. Alright, so we have a pretty much working divider, except for the fact that it block drops. Let's work on the block drop problem, shall we? Let's think, how should we fix the block drop issue? There are a couple ways we can do that. One, we can disable the output of these things and then delay it such that they all fire at when they're supposed to. Now, to do that, we're going to have to do something kind of tricky. I believe... Actually, nah. I don't think we need to. I think we can just delay these lines and then have everything input at the same time, and we should be good. Oh, actually, no. Now that I think of it, what we want to do is we actually want to invert our inputs so that the adders are, all the pistons are on by default, and then turn them off as needed so that everything, the pistons retract when we are calculating, not extend. And the way to do that, I believe, is to have these on by default. So these are on by default. And then when we're calculating, we will, so we'll just have an inverted input. Maybe something like this. Like that. Or something. But these are still kept on by default. Actually, no. That's... No, that'll work. I'm stupid. We keep these... I want to bring this up one, though. Keep these on by default. And then we have our inputs underneath it, just with levers. That'll work just fine. So, levers. Now, as you can see, every single piston in this entire device is on right now. You see that? So, there can't be any block drops when you turn it off, as long as it's timed perfectly. So, when I turn this off, pistons can't block drop when they retract, only when they're extending and retracting really fast. So if we can make sure that the pistons only retract, then we're good. And pistons are instant when they retract, which makes this actually really fast. We can judge the speed based on the pistons. So these adders happen to be 3 ticks when the pistons don't count. So when we are only using the falling edge of the adder, which is what we're using since this is turning off, the pistons are 3 ticks. So we can measure the speed of this thing. We have 3 ticks of the adder, plus this tick right here for this repeater, plus another tick right here for this torch, plus another tick right here for the comparator. So that's 6 ticks total. So between each of these, we need 6 ticks. So let's just add some repeaters. On all of these lines. And also, we will also need to add delay down there too. And on these lines. But let's copy this first. There we go. Copy this around. Boom, boom. Boom. And boom. Yep, that's good. And now under here, actually, we can do this. Haha. Oh, that does make floating redstone. I could paste -A next time, that should work. So that's delayed 6 ticks. Then we have our 7th tick. Wait. So 6 ticks between each unit. That should work, right? Oh wait, no, these need to be 1 tick less since that actually counts on the busing delay. Right. I'm not good with timing, to be honest. So I'm pretty sure that should be good. Probably not, but I'll find out. Yeah, I'll paste these real quick and I'll be right back. Alright, I got these delays on these lines, and I also have the delays on these carryout lines, the lines that connect into these carryouts. So we are almost done synchronizing this thing. The last thing we need to do is delay these lines, the input lines, so that they fire at the same time as everything else. Now to do this, we're going to do something, it's actually really simple. It's a delay line that just activates the inputs as it goes through. So I'm going to be using comparators for this. You'll see what I'm doing in just a sec. Right now it probably won't make much sense. But yeah. That'll be our input. So comparator right here. And right here, this is just to block it. It's a fast AND gate. It works. It's pretty nice. It fits really nicely here. And this, then what we're going to do is we're going to have a line that enables all of these when you hit the lever, basically. So just got to bust these. Alright, this is bust. Now all I have to do is delay this after I connect it to this one. This is going to be enabled at the same time as this line right here, so that it connects properly. So when you enable this line, it enables this top thing to input at the same time and this bottom thing to input at the same time. And everything should be good. So after every enable, you have to add 6 ticks per unit, and the signals should reach just fine. And actually, I believe we are done. So let's name this line something like calculate. Calculate. And then these are our inputs. I'll just label these with normal binary. Oh, that's not the right number. There we go, there we go, there we go, and there we go. Now, let's label our outputs. This is not 9, 8, 4, 2, 1, 0.5, oh, my number pad is disabled, 0.5, and 0.25. Now let's divide something, because everything should be completely synchronized and beautiful. So let's divide 15 by 4, which should be something like 3 point something. Everything happens at the same time, but we do get the wrong answer, unfortunately. But I think I do know what happened. Yeah, that's what happened. Signal strength. See that? Yeah. I believe that can be fixed just by adding a block right here. Yep. So all of these need a block right in front of them. And then it reaches just fine. Alright, so now it should be the right answer, right? Yep, 3.75, right, 3.75. That is indeed 15 divided by 4. Let's do another one. First, let's disable this. Now, when this is disabled, all the pistons retract. It doesn't matter in what order they retract. They can be desynchronized to hell, but since extend. All the pistons extend when you turn that off, and it doesn't matter what order they extend because they could be desynced to hell because at their end state they're extended, which means they can't leave a block behind since they're extended. Let's do 7 divided by. Actually, that's not that interesting. Let's do 5 divided by 2. Nah, 5 divided by 4. Yeah. $1.25. That's 5 divided by 4. So, we have a working divider that can divide into bits beyond the radix point, which is awesome. So we are pretty much done. That was this video. Hope you liked it. Hope you learned how to build a divider. Let's do one more just for lulz. Let's divide 15 by... Let's divide... Trying to think of something fun to do. 15 by 3. Yeah, let's do that. That's an interesting one. That'll be a nice, neat answer too. Bam, bam. 5. 1. And 4. 5 in binary. Alright, so that's my tutorial on how to build a binary divider. I hope you liked it. Hope you learned. This is obviously not the most efficient design in the world, but it brings the point. Puts the point across. This is completely reliable. It should work every time, no matter what, even though it does have pistons, due to the synchronization method that I use here with this control lines. Flood control controls how the signal moves through the pistons to make sure that it doesn't create pulses. And yeah, that's pretty much it for this video. Tell me what you think. How did I do explaining? Is there something you'd like to see explained better, etc.? Leave it in the comments. I'd like to hear it. So yeah, thank you for watching, and I will see you next time.